The winter wind cut different across the Dakota prairie. Anders Larsen learned that his first November in 1880, when ice formed inside his cabin walls and his water bucket froze solid 3 feet from the fireplace. He had built his cabin exactly the way every homesteader in the territory was told to build it. Tight log walls, mud chinking, south-facing door at ground level, standard and proven. By late winter, he had burned through more firewood than 2 men should need, and still the cold poured through every gap. Across the eastern Dakota settlements, other pioneers were fighting the same losing battle in cabins built by the book and failing by the season. Neighbors laughed when Anders started digging a 6-foot hole for what they called his ridiculous underground doorway. Over the next 3 winters, Anders quietly applied an old technique that cut his fuel use by 30% while his neighbors still shivered through cord after cord of wood. What did he understand about trapping cold air that every other settler on the prairie had missed? In this video, I'll break down the exact steps Anders used and the simple physics that made his underground entry save heat when conventional doors failed. The problem revealed itself most clearly at his neighbor Samuel Whitaker's cabin during the blizzard of February 1881. Anders had walked the quarter-mile through knee-deep snow to check on the land office inspector, whose reputation as a veteran builder made his struggles all the more telling. Inside Whitaker's cabin, despite a roaring fire that had consumed nearly half a cord of split oak in 2 days, the temperature never climbed above 28 degrees. Frost coated the interior log walls in a sheet of white crystals, and Whitaker's coffee had developed a skin of ice while he drank it. The door frame, built flush with the cabin's south wall, according to standard homestead manual specifications, leaked a steady stream of Arctic air that pooled around their ankles and crept up the walls like invisible water. Anders watched Whitaker stuff rags and newspaper into the gaps around the door jamb, a ritual the inspector repeated every few hours as the wind shifted and found new pathways through the chinking. The door itself, hung on iron hinges and fitted with a simple wooden latch, opened directly into the main living space with no barrier between the -20-degree outside air and the struggling interior warmth. Each time someone entered or left, the cabin lost what little heat it had gained, and Anders noted that the temperature dropped a measurable 5 degrees with every door opening, requiring another hour of hard firing to recover. This was not an isolated case. Across the scattered homesteads of eastern Dakota Territory, the same scene played out in cabin after cabin built according to the approved methods outlined in the Homestead Act building guides. These manuals, distributed by the land office and trusted by thousands of settlers, specified log construction with walls built directly on stone foundations, doors mounted at ground level facing south to catch winter sun, and gaps between logs sealed with a mixture of mud, grass, and split wood chips. The system seemed reasonable because it used abundant local materials, required manageable labor from a single family, and followed patterns that had worked in the wooded regions of Minnesota and Wisconsin. But the Dakota prairie presented challenges the manual writers had never encountered. Wind speeds regularly reached 40 miles per hour across the flat grassland, driving cold air through the smallest gaps with relentless pressure. The ground froze to depths of 4 feet or more, causing foundation stones to shift and creating new cracks in the chinking each spring. Most critically, the lack of natural windbreaks meant that cabins took the full force of Arctic storms with no protection, and the standard door design offered no defense against this sustained assault. Anders carried knowledge that most of his neighbors lacked. His father, Eric Larsen, had spent 15 years building structures in northern Sweden, where winter temperatures regularly dropped to -40 degrees and stayed there for months. In that climate, Eric had learned a direct entrance was a luxury no family could afford. Swedish builders routinely constructed what they called a kallrum or cold room, a small chamber between the outer door and the main living space that trapped incoming cold air and prevented it from flowing directly into the heated interior. These chambers were often built partially below ground level, taking advantage of the Earth's natural insulation and the tendency of cold air to sink and pool rather than rise. During his first winter in Dakota, Anders had also observed the winter lodges used by the Lakota families who still moved through the territory. An elder named Lone Bear had shown him how their traditional structures incorporated a low entrance tunnel that forced visitors to crawl down and then up into the main chamber. This design, Lone Bear explained, created a cold trap that kept winter wind from rushing directly into the living space. The cold air, being denser than warm air, stayed in the lower tunnel while the heated air remained in the raised interior chamber. When Anders began sketching plans for an underground entry tunnel in the spring of 1881, word spread quickly through the scattered homestead community. Samuel Whitaker stopped by in May to examine the drawings and shook his head with obvious disapproval. "The manual says door at grade level, Anders. Straight and simple. You start digging holes and tunnels. You're asking for cave-ins and flooding." Other neighbors expressed similar doubts. Martha Henley, whose husband had built 3 cabins using standard methods, called the tunnel foreign nonsense and predicted it would fill with snakes and vermin. Even the traveling Methodist preacher, who made monthly rounds to the scattered homesteads, commented that the design seemed overly complicated for simple folk. The mockery intensified when Anders began the actual excavation in late summer. The tunnel design called for a passage 8 feet long and 6 feet deep, angled slightly downward from the outside entrance to a door that would open into the cabin's main room. The work required moving 12 cubic yards of prairie soil, shoring the walls with timber, and installing a drainage system to handle spring snowmelt. Neighbors who stopped to watch the progress often left shaking their heads at what they saw as wasted effort, but Anders understood something his critics missed. The principle he was applying went beyond simple tunnel construction. By carrying the entry point beneath the frost line, he was creating a thermal buffer that would operate according to basic physics rather than fighting against it. Cold air would descend into the tunnel, lose its momentum, and mix with the warmer air that naturally accumulated in the underground space. The earth walls, maintaining a steady temperature near 45 degrees, even in the depths of winter, would moderate the incoming cold before it reached the cabin proper. The result would be an entry system that worked with the prairie climate instead of against it. This principle would soon be tested against the established wisdom of the homestead manuals, and the outcome would determine whether Anders's neighbors continued to burn through precious fuel or learned to build for the reality of Dakota winters. Construction began in earnest during the dry weeks of August 1881, when the prairie soil was firm enough to hold its shape, but not yet frozen. Anders started by marking the tunnel entrance 30 feet from where his cabin's east wall would stand, positioning the opening to face southeast rather than directly south. This seemingly minor adjustment addressed a critical factor that standard door placement ignored. The prevailing winter winds on the Dakota prairie came primarily from the northwest, and by angling the tunnel entrance away from this direction, he could prevent the most brutal gusts from driving straight down into the passageway. The excavation revealed the layered nature of prairie soil that would become crucial to the tunnel's success. The top 18 inches consisted of rich black earth, dense with grass roots that had decomposed over centuries. Below this lay a band of yellow clay, sticky when wet but remarkably stable when properly managed. At the full depth of 6 feet, Anders encountered what local farmers called hardpan, a compressed layer of clay and sand that held water like a bowl but provided an excellent foundation for construction. Working with tools borrowed from Frederick Muller, a Swedish carpenter who had arrived from Wisconsin the previous spring, Anders learned techniques for stabilizing underground construction that went far beyond simple digging. Muller taught him to pack the tunnel walls with a mixture of clay and chopped prairie grass, applied in layers while slightly damp. This plaster created a surface that resisted both cracking and water infiltration, essential for a structure that would face repeated freeze-thaw cycles. The clay mixture also provided thermal mass that would store and release heat more gradually than bare earth, moderating temperature swings in the tunnel space. The floor construction required particular attention to drainage and thermal properties. Anders laid a foundation of flat field stones, fitted tightly together and sloped at a gentle angle toward a drainage channel that led away from both the tunnel and the cabin site. Over these stones, he spread a layer of sand mixed with powdered clay, tamped solid, to create a surface that would shed water while maintaining structural integrity. This floor design drew from techniques Muller had observed in Scandinavian root cellars, where proper drainage meant the difference between a useful storage space and a flooded pit. The tunnel walls required timber reinforcement to prevent collapse, but Anders discovered that the specific placement of these supports affected the tunnel's thermal performance. Rather than using conventional vertical posts, he installed horizontal log sleepers every 3 feet along the walls, creating small air pockets between the logs and the clay-packed earth. These air spaces acted as additional insulation, slowing the transfer of cold from the surface down to the tunnel floor. The technique came from his observation of how Lone Bear's people constructed their winter lodges, using layers of different materials to create barriers against cold penetration. Installing the outer door presented its own engineering challenges. The door itself, built from thick oak planks and hung on iron hinges obtained from the territorial supply depot, had to seal against both wind and moisture while operating smoothly in conditions that could range from summer heat to winter cold of -30 degrees. Anders positioned the door frame 18 inches back from the tunnel entrance, creating a small vestibule where snow could accumulate without blocking the door's swing. He also angled the door slightly inward at the top, a detail that prevented rain and snowmelt from running directly onto the hinges and latch mechanism. The most innovative aspect of the design involved what Anders called the wind baffle, a series of horizontal logs positioned inside the tunnel to break up air currents without blocking passage. These logs, each about 18 inches long and 6 inches in diameter, were mounted on wooden brackets attached to alternating walls. A person entering the tunnel had to step around them in a slight zigzag pattern, but the baffles forced incoming air to change direction multiple times before reaching the inner door. This disrupted the laminar flow that allowed cold air to rush directly from outside to inside, instead creating turbulence that dissipated the cold air's momentum and allowed it to mix with the warmer air already present in the tunnel. Testing the system required patience and careful measurement. During the mild cold snap of November 1881, when outside temperatures dropped to 15 degrees for 3 consecutive nights, Anders used a thermometer borrowed from the territorial doctor to record conditions at various points in the tunnel. The outer vestibule averaged 28 degrees, the midpoint of the tunnel held steady at 35 degrees, and the area just outside the inner door maintained 41 degrees. Meanwhile, Samuel Whitaker's cabin, with its conventional door opening directly to the outside, showed interior temperatures that fluctuated wildly with each gust of wind. The true test came during January 1882, when a sustained cold spell brought temperatures down to -25 degrees and held them there for a week. Anders documented fuel consumption carefully, burning 1 1/3 cords of split oak to maintain comfortable interior temperatures. Whitaker, in his standard cabin of similar size, consumed 2 1/2 cords during the same period, and still complained of drafts and cold spots throughout his living space. More significantly, the tunnel demonstrated its effectiveness in managing the transition between outside and inside conditions. Each entry through a conventional door created what settlers called a cold shock, a sudden rush of frigid air that could drop interior temperatures by several degrees and take an hour or more to recover. The tunnel system eliminated this problem entirely. Cold air entering the outer door sank to the tunnel floor and mixed gradually with warmer air, so that by the time someone reached the inner door, they brought with them air that was already partially warmed by the earth and the thermal mass of the clay walls. This principle of staged temperature transition would prove essential when combined with improvements to the cabin structure itself, but those developments would require additional techniques that went beyond foundation and entry design. The failure of Martha Henley's cabin wall during the March thaw of 1883 revealed a fundamental problem that Anders had not yet addressed. Despite his successful tunnel entry, his own cabin walls were built using the standard single log method, and they showed the same weaknesses that plagued every other structure in the territory. The logs had shrunk during their first winter, creating gaps up to 1/2 inch wide in some places. The mud chinking had cracked and fallen out in chunks, leaving openings that allowed both air infiltration and moisture penetration. Most critically, Anders discovered that heat was escaping through the log walls themselves at a rate that no amount of fuel could overcome. Frederick Mueller provided the solution during a visit in April, when he examined Anders's cabin walls with the practiced eye of someone who had built structures in Wisconsin's harsh climate. Mueller explained that single log construction, while adequate for milder regions, simply could not provide enough insulation for Dakota's extreme temperature swings. In northern Wisconsin, he had learned to build what German settlers called Doppelwand construction, using two parallel walls with an insulated space between them. This technique created a thermal barrier that dramatically reduced heat loss while providing structural strength superior to single wall building. The double wall system required precise planning and considerably more materials than standard construction. Anders began by laying out two parallel foundation lines, each consisting of carefully selected field stones elevated 6 inches above ground level. The inner wall would use logs 12 inches in diameter, while the outer wall used slightly smaller logs of 10 inches diameter. The space between the two walls measured exactly 1 foot, creating a cavity that would be filled with insulating material. This air gap was critical because it interrupted the direct conduction of heat from inside to outside that occurred in solid log walls. Preparing the insulating fill required harvesting and processing prairie grass during the dry season of late summer 1883. Anders cut mature grass stems when they were fully dry, but before the autumn rains, bundling them into tight sheaves and storing them in his lean-to until needed. The grass had to be chopped into sections roughly 4 inches long using a hay knife, then mixed with a small amount of lime to discourage insects and rodents. This chopped grass, when packed tightly into the wall cavity, created thousands of small air pockets that trapped heat while allowing moisture to escape gradually rather than accumulating and rotting. The construction sequence proved as important as the materials themselves. Anders built both walls simultaneously, laying logs in matched courses and maintaining the precise 1-foot spacing using temporary wooden spacers. Every third course, he installed tie logs that spanned from the inner wall to the outer wall, binding the structure together and preventing the walls from spreading under the weight of the roof. These tie logs were carefully sealed where they passed through the insulation cavity, using a mixture of pine pitch and oakum that Frederick had brought from Wisconsin. The elevated sill design addressed a problem that had plagued prairie cabins since the first homesteaders arrived. Ground-level sills allowed moisture to wick up into the logs from snow and rain, causing rot and providing a pathway for cold air to infiltrate under the floor. By raising the sill 6 inches on stone foundations and treating the contact points with tar and pine pitch, Anders created a moisture barrier that also eliminated a major source of heat loss. The sill itself was hewn from oak logs and sized to support both the inner and outer walls plus the structural loads from the roof system. Installing the insulation required techniques that went beyond simply stuffing grass into the cavity. Anders learned to layer the material in lifts of 6 inches, tamping each layer firmly, but not compressing it so tightly that air could not circulate. He also discovered the importance of maintaining consistent density throughout the cavity. Areas that were packed too loosely allowed convective air currents to develop, reducing the insulation's effectiveness. Sections that were compressed too tightly became thermal bridges that conducted heat directly through the wall system. The interior finish provided another opportunity to improve thermal performance through thermal mass. Rather than leaving the inner logs exposed, Anders applied a coating of clay plaster mixed with chopped straw and sand. This plaster, laid on in 2 coats to a total thickness of 1 inch, served multiple functions. The clay absorbed heat during the day when the stove was burning actively, then released this stored heat gradually during the night as interior temperatures began to drop. The thermal mass effect moderated temperature swings and reduced the sharp peaks and valleys that characterized poorly insulated buildings. Mixing the clay plaster required specific proportions that Frederick had learned through trial and error in Wisconsin. The base consisted of clay-rich soil dug from a deposit 3 miles south of Anders's homestead, where a seasonal creek had deposited fine particles over many years. To 1 part clay, Anders added half a part clean sand and 1/4 part chopped straw, along with enough water to create a mixture that could be applied with a wooden float but would not sag or crack as it dried. The first coat was applied roughly to provide bonding to the log surface, while the second coat was worked smooth and allowed to cure slowly over several weeks. Testing the completed wall system during the winter of 1884 provided dramatic evidence of the double wall's effectiveness. Using thermometers placed at various points through the wall thickness, Anders measured temperature gradients that revealed how the insulation was performing. On a day when outside temperature reached minus 15 degrees and inside temperature held at 55 degrees, the outer wall surface measured 8 degrees, the insulation cavity averaged 32 degrees, and the inner wall surface maintained 48 degrees. The clay plaster showed the least temperature variation, confirming its role as thermal mass. More importantly, fuel consumption data showed the practical benefits of the new construction. Anders burned 1 1/4 cords of wood during January 1885, compared to the 2 3/4 cords that Samuel Whitaker consumed in his single-wall cabin of nearly identical size. The double-wall construction had reduced heating requirements by more than 50%, while providing dramatically improved comfort levels and eliminating the cold drafts that made standard cabins nearly uninhabitable during severe weather. The crisis emerged during the warm spell of March 1885, when Anders discovered that his well-insulated cabin had developed an unexpected problem. Ice crystals covered the interior surface of his north wall each morning, and a musty smell indicated that moisture was accumulating faster than it could escape. The very effectiveness of his double wall system and tunnel entry had created a nearly airtight environment where water vapor from cooking, breathing, and the wood stove had nowhere to go. Samuel Whitaker, visiting to examine the ice formation, pointed out that his own drafty cabin never suffered from condensation because cold air was constantly entering and displacing the moist interior air. The problem intensified as Anders observed the long-term effects of trapped moisture on his carefully constructed walls. The clay plaster began to show dark stains where water vapor was condensing and soaking into the surface. More critically, he noticed that the logs themselves were beginning to shrink unevenly as moisture content fluctuated between the dry winter air and the humid conditions that developed whenever he cooked or heated water. The chinking between logs, which had remained tight throughout the previous winter, started to crack and separate as the wood movement exceeded what the clay and grass mixture could accommodate. The solution came from an unexpected source during a late spring visit to Lone Bear's winter camp. The Dakota elder had constructed a temporary lodge that demonstrated sophisticated principles of air management that went far beyond simple shelter. The structure featured a carefully designed ventilation system with a low opening near the floor on the windward side and a high opening near the smoke hole that could be adjusted with flaps depending on weather conditions. Lone Bear explained that stagnant air inside a sealed lodge would quickly become unhealthy and would also cause structural problems as moisture accumulated in the hide coverings and wooden framework. More significantly, Lone Bear showed Anders how the controlled movement of air through the lodge created what he called breathing walls that stayed dry and flexible rather than becoming brittle from alternating wet and dry cycles. The key principle involved creating a gentle but continuous air movement that carried moisture away before it could condense on surfaces, while avoiding the strong drafts that would make the interior uncomfortable and waste fuel. This required precise positioning of inlet and outlet openings to take advantage of natural air currents and pressure differences. Adapting this principle to log construction required careful engineering of ventilation openings that would not compromise the structural integrity or thermal performance of the double wall system. Anders began by installing a fresh air intake in the outer vestibule of his tunnel entrance, positioning a 4-inch diameter wooden pipe that extended from the tunnel floor up through the prairie surface at ground level. This pipe was fitted with a hinged damper that could be adjusted to control the volume of incoming air, and the opening was protected with a wooden hood that prevented rain and snow from entering while allowing air to flow freely. The exhaust system proved more complex because it had to remove stale air without creating excessive heat loss. Anders installed a 6-inch diameter pipe that ran from a point near the ceiling of his main room up through the roof ridge, using techniques Frederick Mueller had observed in Wisconsin brewery construction, where controlled ventilation was essential for fermentation processes. The pipe was fabricated from fitted wooden staves, sealed with pine pitch, and insulated where it passed through the roof to prevent condensation from forming inside the ventilation system itself. The critical innovation involved creating a damper system that could modulate ventilation based on outdoor temperature and wind conditions. During severe cold snaps, the dampers could be nearly closed to minimize heat loss while still allowing enough air movement to prevent moisture buildup. In milder weather, the dampers could be opened wider to increase air circulation and remove cooking odors, excess humidity, and the combustion byproducts from the wood stove. Anders constructed the dampers using thin wooden discs mounted on iron rods with leather gaskets to ensure tight sealing when closed. Managing water infiltration from precipitation required addressing the cabin's relationship with its immediate environment in ways that standard construction ignored completely. Anders extended his roof overhang to 2½ feet beyond the wall line on all sides, using techniques that Frederick had learned from barn construction, where protecting stored materials from moisture was critical for farm operations. The extended overhang required additional structural support, achieved through the installation of wooden brackets that transferred roof loads directly to the double wall system without creating thermal bridges. The roof drainage system incorporated stone drip courses positioned at the eaves to direct water away from the log walls and foundation. These drip courses consisted of flat field stones, each about 12 inches long and 4 inches wide, mortared together with clay and positioned to create a slight downward slope. Water running off the roof would hit the stone surface and be directed away from the building, rather than running down the log walls where it could penetrate the chinking or create ice dams during winter weather. Ground-level moisture management required creating a drainage system around the cabin perimeter that would handle spring snowmelt and summer rainfall, without allowing water to accumulate near the foundation. Anders dug a shallow trench, 6 inches deep and 8 inches wide, completely around the cabin, maintaining a gentle slope that directed water toward a natural drainage swale 200 feet to the south. The trench was filled with graded gravel that allowed rapid water infiltration while providing a stable surface that would not erode during heavy rains. Testing the complete ventilation and moisture management system during the variable weather of spring 1886 provided clear evidence of its effectiveness. Anders used strips of cloth hung near the ventilation openings to monitor air movement, observing that fresh air entered through the tunnel intake, circulated through the main living space, and exited through the roof vent in a steady but gentle current. A thermometer placed in the exhaust pipe showed that outgoing air was typically 10 to 15 degrees warmer than incoming air, indicating that the system was removing stale air without excessive heat loss. More importantly, humidity measurements using wet and dry bulb thermometers borrowed from the Territorial Weather Observer showed that interior humidity levels remained stable at 35 to 40% throughout the spring months, compared to readings above 60% in neighboring cabins that lacked controlled ventilation. The stable humidity levels eliminated the condensation problems that had plagued the cabin during its first winter of operation, and visual inspection revealed no moisture damage to the clay plaster or log surfaces. The integrated system of controlled ventilation, extended roof protection, and perimeter drainage transformed the cabin from a structure that simply resisted the weather into one that actively managed its environment, creating conditions that preserved both comfort and structural integrity while maintaining the fuel efficiency that made frontier life sustainable. The winter of 1889 brought weather that tested every structure on the Dakota prairie beyond its design limits. The cold arrived in December with sustained temperatures that dropped to minus 30 degrees and stayed there for weeks. But the real trial began on January 15th when a high-pressure system from the Arctic settled over the territory and refused to move. For 4 consecutive nights, temperatures plunged to minus 40 degrees, with wind chills that the Territorial Weather Observer calculated at minus 65 degrees. The sustained cold was unlike anything the homestead community had experienced, and it revealed the true differences between building systems that had seemed merely preferential in milder conditions. Samuel Whitaker's cabin, representing the standard construction that most settlers had trusted for nearly a decade, failed catastrophically during the second night of the cold snap. Despite burning oak logs continuously in his fireplace, the interior temperature dropped to 8 degrees by dawn, and ice formed on the interior walls thick enough that Whitaker could scrape it off with a knife. The door frame had contracted so severely that gaps opened around the entire perimeter, allowing a steady flow of Arctic air that no amount of fuel could overcome. By the third day, Whitaker had consumed nearly 2 full cords of his winter wood supply, yet the cabin remained barely habitable. The structural damage extended beyond simple discomfort. The rapid temperature changes caused the logs in Whitaker's walls to crack along their length, creating new pathways for air infiltration that would persist long after the cold snap ended. The chinking between logs had fallen out in large sections, leaving gaps up to 2 inches wide in places. Most critically, the floor joists had contracted and shifted, causing the floorboards to buckle and creating an uneven surface that would require complete reconstruction to repair properly. Anders documented his cabin's performance with measurements that revealed how each component of his integrated system contributed to the overall success. Throughout the 4-night cold spell, his interior temperature never dropped below 38 degrees, even when the wood stove was allowed to burn down to coals during the late night hours. The tunnel entry system proved its worth during this extreme test, as the buried passage maintained an average temperature of 22 degrees even when outside air reached -40. This meant that anyone entering the cabin brought air that was already 62 degrees warmer than the exterior conditions. The double wall construction demonstrated thermal performance that exceeded even Anders's expectations. Temperature measurements taken through holes drilled at various points showed that the outer wall surface averaged -32 degrees, while the inner wall surface maintained 42 degrees, a differential of 74 degrees across just 14 inches of construction thickness. The prairie grass insulation had remained dry and effective, with no settling or compression that would have reduced its thermal resistance. The controlled ventilation system managed to maintain air quality without excessive heat loss, even under these extreme conditions. Anders had partially closed the dampers to reduce airflow, but enough ventilation continued to prevent moisture buildup and maintain breathable air. The exhaust air temperature averaged 15 degrees warmer than the intake air, indicating that the system was removing stale air while recovering most of the heat energy that would have been lost through uncontrolled air leakage. Fuel consumption provided the most dramatic evidence of the system's effectiveness. Anders burned 1 3/4 cords of wood during the entire 4-night period, compared to Samuel Whitaker's consumption of nearly 4 cords for the same time frame. More importantly, Anders's fuel burned efficiently and provided consistent heat, while Whitaker's constant firing was largely wasted trying to overcome heat loss through the building envelope. The news of these performance differences spread rapidly through the scattered homestead community. Martha Henley arrived on the 5th day to examine Anders's construction methods, bringing with her a delegation of neighbors whose own cabins had suffered various degrees of damage during the cold snap. They found Anders's cabin structurally sound, with no cracked logs, failed chinking, or floor movement. The contrast was so stark that several homesteaders asked to measure the wall thickness and examine the tunnel entry system for themselves. Frederick Muller, whose own cabin had incorporated some of Anders's techniques but not the complete system, documented the differences in a letter to his brother in Wisconsin. Muller's cabin, built with double walls but lacking the tunnel entry and controlled ventilation, had performed better than standard construction, but still consumed nearly 3 cords of fuel and experienced some structural movement. This partial success helped demonstrate that the individual techniques worked best when combined into an integrated approach rather than applied piecemeal. The validation extended beyond immediate neighbors to official recognition from territorial authorities. Mary Hawkins, who had recently been appointed as the county homestead advisor, visited Anders's site in February 1890 to evaluate construction methods that might be recommended to new settlers. Her official report, filed with the Territorial Land Office, specifically mentioned the underground entry tunnel as a technique that substantially reduces heating fuel requirements while providing superior weather protection. The adoption of Anders's methods began gradually, but accelerated as word spread about the performance advantages. 3 homesteaders building new cabins in spring 1890 incorporated tunnel entries into their designs, working with Frederick Muller to adapt the construction techniques to their specific sites. 2 existing cabin owners retrofitted their structures with extended roof overhangs and perimeter drainage systems, finding that even these partial improvements provided measurable benefits. By 1892, the integrated building approach had evolved into a recognized alternative to standard homestead construction. A circular distributed by the Territorial Agricultural Extension Service included detailed drawings of underground entry design and double wall insulation methods, crediting the techniques to proven performance in extreme Dakota weather conditions. The document noted fuel savings of 30 to 40% compared to conventional construction, figures that made the additional labor and materials economically attractive despite higher initial costs. The long-term legacy became evident in the structures that survived into the 20th century. A survey conducted in 1920 by the State Historical Society found that cabins built using variations of Anders's methods showed significantly less structural deterioration than standard construction from the same era. The underground entries remained functional and weathertight. The double walls maintained their insulation properties, and the controlled ventilation systems continued to manage moisture effectively decades after their installation. The principles Anders had demonstrated proved applicable far beyond the specific conditions of Dakota Territory homesteading, influencing building practices throughout the northern plains and establishing techniques that would be rediscovered and refined by later generations of builders facing similar challenges in harsh climates.